Hello and welcome to this course on heat transfer. This is a typical undergraduate course on heat transfer which is in the Department of Mechanical Engineering at most universities and colleges. Heat transfer also is taken by students in aerospace and chemical engineering, probably even metallurgy. Of course, certain contents would be slightly different from what is done in mechanical engineering. But by and large, essentially, we would be dealing with conduction, convection, and radiation heat transfer, and some applications like heat exchangers. Some colleges or syllabi would have boiling and condensation introduction also. So, in this course, we are going to be dealing primarily with conduction, convection, and radiation, and couple of lectures on one very practical application of heat transfer, which is heat exchanger. So this is about 60 half an hour lectures, 61 half an hour lectures that would be there as a part of this course. And roughly we have thought of doing about 18 half an hour lectures on conduction, probably about 17 or 16 on convection, and 3 on heat exchangers, and the remaining on radiation heat transfer, natural convection also. So, what is heat transfer? Why should we study heat transfer? All these things we would try to understand in today's basic introduction lecture. So, what is heat transfer? Heat transfer has been there in our everyday life from time immemorial. Heat is going to be transferred whether we like it or no when there is a temperature difference. So, we have heat transfer in our everyday life, boiling of water, making tea, drying of clothes, heat coming from the sun to the earth, and cooking, washing, and heat geyser for hot water. So many applications. Of course, in manufacturing sector, etc., there's a lot of heat transfer. You have combustion, you have nuclear reactors where there is heat transfer, you have propulsion systems where there is heat transfer, you have very low temperature systems, there also there is heat transfer. So the subject of heat transfer finds application almost in every aspect of engineering everyday life, and therefore we have to study it. Now, right from our high school classes 8, 9, wherever we got introduced to heat transfer, we were told that there are primarily 3 modes of heat transfer: conduction, convection, and radiation. And conduction is where energy is transferred by because of finite temperature difference by molecular vibrations, etc. So it's like passing the parcel. So you stand in a line and a parcel is moved from the leftmost person to the rightmost person. The leftmost corresponds to the wall at a higher temperature and the right one is to a wall at lower temperature, and the molecules which are vibrating more because of high energy, because of the higher temperature, keep on transferring energy to the subsequent molecules, and energy heat is transferred from high temperature to low temperature. Convective heat transfer, on the other hand, if it's a moving fluid, so conduction is primarily in a stationary fluid or a solid. Convection is both. Advection will define it in a more systematic manner, but convection is where there is actual motion of the fluid. So if you are trying to boil water for tea, or you have made some mixture which is getting heated from the bottom, we always keep on stirring it because we want the temperature to become uniform throughout. So the bulk motion, the actual motion of the fluid, is causing the heat to get transferred. So it's like passing the parcel with the people also moving. So let's say you're moving in a circle and you have to pass the parcel also. So there is motion of the fluid element and also transfer of energy. And of course, radiation, everybody knows how heat is transferred from the sun to the earth. You don't require a medium, it's in the form of electromagnetic waves, so on and so forth. So because it is so widely prevalent, we have to understand how heat is being transferred and why and how is it different from thermodynamics. In thermodynamics, for example, we looked at the first law. For example, first law of thermodynamics, we would write dE by dt is equal to q dot cv minus w dot cv plus summation of mass flow inlet hi plus vi squared by 2 plus gzi. You may have a slightly different form for this, but broadly this is the nature of the equation that we would see in the first law of thermodynamics. And what did we say? We would say, okay, this is heat transferred and this is the work done, and as we would say, this would be given as a number. A number would be specified. So if you talk of a turbine, heat lost by the turbine is Q out, you would say 500 watts. So it's a number that is given to you. It's not how this heat was lost, whether it was through convection or radiation. Thermodynamics did not care. Thermodynamics said this is a number, take it. This is heat lost. So now in heat transfer, what we would do is we'll say, okay, how is this heat going out? Whether it is 500 watts or 490 or 520, we will find out ways and means to calculate this particular quantity. So we would say, okay, heat is going out, fine. How does it go out? Is there convection? H comma T infinity, we'll understand what these are. This is representing convection. Is there an emissivity for the surface? Is there radiation heat transfer which is occurring? So heat is going out by convection plus radiation. We will calculate these two quantities and then see whether it is coming out to be 500 watts or whatever is the number. And that is where heat transfer is coming into play. Thermodynamics gave me this as a black box. Okay, whereas this now is going to be solved, it's going to be calculated using various methods which we'll study as a part of this course. Okay, so let's just move further. Of course, we said due to temperature difference has to be there for any heat to be transferred. So if there is no temperature difference, there is no heat transfer in whatever mode. And what is conduction? As we said, it's a heat transfer through a solid or a stationary fluid. So due to molecular vibration, and we will go into the details in a bit. What is convection and then what is radiation? So we'll start with conduction. Conduction essentially refers to, so if I have two walls which are at temperature, the entire wall is at temperature T1, this is at a temperature T2. Let us say this is the window, outside is minus 10 degrees, inside is 30 degrees. So you have a solid wall, which is the brick wall or the window, which is going to prevent, allow heat transfer from the room to the outside. Obviously, we know that if the room is at 30 and the outside is at minus 10, heat is going to flow from high temperature to low temperature. That is the direction of heat flow. This is direction of heat flow. Correct? So if this entire wall is at T1 and let's say T1 greater than T2, the area required for heat transfer. So this is the area which I am talking about. And if I say the direction of heat flow is perpendicular to this surface, orthogonal or perpendicular to the surface. So T1 greater than T2, let me put this coordinate system here, x, this is x is equal to L and this is x equal to 0. So what does conduction, how does conduction happen and what does the law governing conduction say? Q is the heat transfer rate, which is given as joules per second, which is also watt. This is seen to be proportional to the area available, and this is common sense. If I have a big window Okay, the window is, the larger the dimensions of the window, greater is the heat loss from the room. So Q is directly proportional to A. Okay, so if I have a thicker wall versus a thinner wall, thicker wall will offer more resistance to heat transfer, because we would see from observations that lesser amount of heat is going to flow. That's why you will wear multiple layers. You will have a shirt, you will have a sweater, you would have a jacket when you are going out in cold climates. You would not have one thick jacket, you would have multiple layers. So larger the thicknesses, you would have greater the resistance to heat transfer. So Q is inversely proportional to the thickness, which is L here, L minus 0, which is L, and Q is directly proportional to the temperature difference. Larger the temperature difference, greater is the heat transfer. When you have the outside at minus 20 and the inside is 50, the heat transfer would be more. Furnace, for example, the inside of the furnace would be at 1200, 1500 Kelvin, the outside room would be at 30 degree, or the lab would be at 40 degrees. The heat transfer rate would be very high because the delta T is very high. Now if I combine all this, Q is proportional to A delta T by L, and this proportionality is replaced by an equality which says Ka delta T by L. This K is called as thermal conductivity. It is a material property. So, material property, because how much heat is going to flow is dependent on which material you are having. For example, all of us would have seen or also know that copper is a very good conductor of heat. Stainless steel comes later, aluminum is somewhere in the middle. Thermal conductivity decides how fast or how slow the heat is going to get transferred. So if I have a pan, for example, this is made of copper bottom, you don't have the handle made of copper. You have the handle made of typically wood. Why? Because when this pan gets hot, the handle still has to remain cold. That means wood, though the heat is coming onto the pan, very less heat is coming to the wooden handle. Therefore, this wood is probably going to have a very different value of thermal conductivity, which is a material property, compared to copper, which has a very high value. And so for example, so we wrote Q is equal to Ka delta T by L. I'm just going to use this again with some more explanation. This is X, this is L, and T1 is larger than T2. This wall is at T2. So T1 greater than T2, we would say the heat is flowing in the direction of decreasing temperature. Am I right? Temperature is decreasing from left to right, heat is flowing from left to right. So if I want to write dt by dx at the gross level, this is nothing but T2 minus T1 divided by L minus 0, and T2 is smaller than T1, therefore dt by dx is always less than 0. Therefore, to make Q positive, we introduce a negative sign. Because dt by dx is less than 0, therefore Q would be written as minus Ka dt by dx, and this represents what we call as Fourier's law of heat conduction. Fourier's law of heat conduction. Ka dt by dx with the minus sign. The minus sign is added because dt by dx is inherently negative. Heat flows from high temperature to low temperature. The surface T2, surface at T2 is going to be always smaller than surface at T1. T2 is going to be smaller, therefore heat has to flow from left to right. This is Fourier's law. And what do we say? K is thermal conductivity. Units we can say Q is in watts, area is in meters squared, and temperature is delta T is Kelvin per meter. Therefore, the units for K is nothing but watt per meter Kelvin. SI units for thermal conductivity is watt per meter Kelvin. Typically, copper will have about 400 aluminium about 200, stainless steel about 15 to 18. This is the typical values of thermal conductivity, watt per meter Kelvin. And wood, etc., or insulating materials like wood, glass, wool, all these are typically poor thermal conductivity material, poor values of K. Sorry, I should write low values of K, therefore insulators. Okay, so this is Fourier's law, this is conduction. And what do we say? dt by dx is typically going to be, we'll see later on, we would have a temperature drop which is linear. So this is a temperature variation, dt by dx, dt dx would be negative, and q by ka, a is area normal or orthogonal to the surface. So two walls, this is the area for heat transfer. Okay, next we come to convection. Convection is typically given by Q is equal to H into surface area into T wall minus T infinity, T wall or T surface. What is this? This is called as the Newton's law of cooling. All of you would have probably even done an experiment in the 11th or 12th standard where you heat something and you allow it to cool. So you heat a ball or a metal plate in some furnace or something and allow it to cool in air and note down the temperature at various instants of time, and you will plot temperature as a function of time to do something like this. And if this is your room temperature, T room is equal to say 30 degrees, the gradients would be highest initially, and as I move closer and closer to the room temperature, the cooling rate will become very small. And this you would have seen, very important, that the object may reach 35, but from 35 to 30 it will take very long time, whereas from 70 to 30 it would take much faster to cool. So this is basically convection, where heat transfer is occurring because of bulk mixing of the fluid. What do I mean by that? So when I have a heated plate, so this is at T wall or surface temperature or wall temperature, and let us say T wall is greater than T infinity, where T infinity is called as the surrounding temperature or ambient temperature. So this is T infinity, and there is flowing of air or whatever is the medium. So you have a cup of coffee and the fan is on and you are expecting it to cool, or you have cooked something like potatoes you have boiled and you want them to cool. So what is the first thing that we do? Either we put them in cold water or we put it under, spread it and put it under the fan for it to cool. That's essentially what is happening. The air near the hot surface will become hotter, and therefore its density would become lesser. It will rise. The colder air from the top will come and replace this, and this is essentially how the currents are generated. So when there is help because of a fan, we call it as forced convection. Forced convection is where the mechanism of heat transfer is aided by fan or blower, etc. Natural convection or free convection is where we do not have any external means to aid the flow. For example, no external means. You just leave a cup of coffee to cool on its own. It will take very long time to cool, but it will cool. Okay, so or you have your agarbatti or incense stick. When it burns, you have smoke which is going to come out like this, and it would just diffuse into the room. It just diffuse into the room. Okay, nothing is aiding the motion. It is just the heat that the fumes are going to carry, and eventually after a while it will just diffuse into the room. You will not even see this. So natural or free convection is going to occur at all times in nature. This will be there. You can't prevent it. Okay, so this is natural. Okay, forced convection you can add by having a fan or a blower. So imagine I have a fan here, the agarbatti is burning. The breeze will make the convection much faster. So it would appear as if natural convection doesn't exist. But please remember, in nature, natural or free convection always exists. Its contribution may become very negligible when forced convection is there, but that doesn't mean it goes to zero. Forced convection can go to zero because there is nothing which is aiding, but natural convection can never be zero as long as there is a temperature difference. The rate of heat transfer, the Q due to natural convection, may be much less than Q due to forced when forced convection is there. Therefore, we may neglect. When forced convection is there, this can be neglected, but doesn't mean that it's an approximation. Okay, so it's something which you will see when to take natural convection into account, when to neglect it. We'll see that also. The H that we see, Q is equal to HA delta T. This H is called as the heat transfer coefficient. Its units you can check. Q is watts, this is meter square, this is Kelvin. So H would be watt per meter squared Kelvin. Units for H. Now this is depending on the fluid. Of course, whether it is air or water or kerosene or whatever, it depends on the material. Nature of flow. Yes. The amount of heat transferred when I have suppose I have this hot potato. Potato is at 70 degrees centigrade. If I allow it to cool in air at 30 degree, case 1, case 2 is water at 30 degree. Okay. I'm having two identical potatoes, just heated to 70 degree, taken out from a pressure cooker, and I want to cool it. Whether I cool it in air, stagnant air, just leave it in the room at 30 degree, or put it in a water bath at 30 degree, which will cool faster. We know this will cool faster. If I also, this is now still air, this is still water. Another experiment I do, which is flowing air at 30 degree, flowing water, tap water you run and you wash it. So let me just use another color here. So this is case A, this is case B, this is case C, and this is case D. We know that this is going to be the worst case. It will take long for it to cool. This is slightly better. This is the best flowing water. Under running tap water you keep. When you get some steam burn or something, it's always told, put it under running water. Because running water takes away heat very quickly. That means this H, which is Q, is the rate, okay, how fast heat is being removed per unit time. This Q will be higher for given A and delta T when H is high. Correct? What is A? Surface area of potato. This is your surface area. That is fixed for the potato. Temperature T wall 70 and T surrounding 30. That is also fixed, delta T. So when these two numbers are fixed, if I want the heat to be removed fast, H has to be high. Which case is H high? This is the best case. This is the worst case. These two are intermediate cases. So in general, I can write H natural convection for gases less than H natural convection for liquid. H natural convection in general is less than H forced convection. and of course if you have phase change or boiling or condensation, that would be the highest heat transfer. So let me just go back to the slides and see what is there. So we have told all this. I'll come to this, and bulk motion, we have covered this part also. So Q double prime is essentially heat flux. So heat flux is heat transfer per unit surface area. So the surface area is this one. So Q divided by A for this is called as a plane wall geometry. So you take a wall, outside wall of the house is a plane wall. So this wall has a finite thickness, the area is A. Q divided by A, both sides the area is constant. At every plane inside the wall the area is the same. So Q divided by a constant is heat flux, watt per meter squared. Dt by dx we have shown. So Q double prime is K into delta T by L. I'll come back to this problem. Convection, force, natural convection, water boiling, condensation. So Q is positive when heat is transferred from the surface, negative when heat is transferred to the surface, because the sign would be appropriately changed. Heat transfer coefficient is a function of surface geometry, nature of flow and fluid. Here are the values. Typically 2 to 25 is the heat transfer coefficient for gases. For liquids it is 50 to 1000. Forced convection gases would be about 25 to 250. Liquids is 50 to, you could have very high heat transfer coefficients, but typically single phase and if you're talking of water etc., you would get around 400 300 watt per meter square Kelvin. Boiling and condensation provide very large values of heat transfer coefficient. So I'll just go to the conduction problem for you. So this is a wall of an industrial furnace constructed with 0.15 meter thick fire clay brick having thermal conductivity so and so. Measurements during steady state operation reveal 1400 Kelvin and 1150 as the inner and outer wall temperatures. What is the rate of heat loss for a given wall whose dimensions are given? So we have a wall and we have two temperatures prescribed, one at the left end and the other at the right end of the wall, and the wall has a finite thickness which is given to me 0.15 meter. The dimensions of the wall are given, so the area is given to me. So we have to calculate the heat loss. So essentially it's a simple 1D conduction problem. We are talking of steady state condition, which means whatever is happening at every instant of time. The temperatures remain at 1400 and 1150 Kelvin, and the heat is just going to be removed exactly the same way. So Q is K into delta T by L. So I use 1400 minus 1150 divided by the magnitude of the thickness, which is what is delta T by L. Now if I want to use Fourier's law as minus Ka dt by dx, then I should say dt by dx means 1150 minus 1400, T2 minus T1 divided by x2 minus x1. x2 is 0.15, x1 is 0. The number will come negative, therefore the minus sign there in front will take care of it. You can just do it as the magnitude of delta T and magnitude of the thickness and be done with it as it is done here. So K is known, area is width into height, 3 into 0.5, that's known. So I could just use it in one step. Q double prime into A is Q, Ka delta T by L, which is 4250 watt. What are the assumptions here? Very important. Steady state, as I said, whatever is happening now is going to happen at every instant of time. 1D heat conduction through this wall. Heat is only being transferred from left to right and not going vertically up or into the plane of the board. The value of thermal conductivity is treated as constant. Okay. Now boundary layer in convection, we will see from fluid mechanics what a boundary layer is. Region close to the wall where the velocity is going to change. In heat transfer, region close to the wall where the temperature is going to change is called as a thermal boundary layer. And consider a human body, so which is like a cylinder. You are supposed to calculate the heat transfer. The surface area is given, the heat transfer coefficient is given, the body temperature and the ambient temperature are given. H is known, A is known, delta T is known. You have to calculate the heat transfer coefficient. So surface area, all the quantities are known. You can calculate it as 180 watts. Last but not the least, what is radiation? Radiation is emitted by matter which is at a finite temperature. Any body above absolute zero emits radiation. So it is transported in the form of electromagnetic waves. No medium is required. And we know again from high school, emissive power, the amount of energy emitted per unit area of any body, which is nothing but sigma into T to the power 4. This is emissive power. It is just E, not E sub B. So E sub B would be for a black body. So sigma T to the power 4 is what is the energy emitted. Sigma is called as Stephen Boltzmann constant, which is nothing but 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay, any body would be this. We will introduce a concept called emissivity, which is black surface sigma T to the power 4, real surface emissivity times sigma T to the power 4. What is emissivity? Emissivity is representing how far a real surface is from a quote unquote idealized body or a black body. Emissivity goes from 0 to 1 for any surface. It could be a constant or a function of temperature. If I take any surface, this surface, for example, is at a finite temperature Ts, has emissivity E, epsilon. Capital E is the emissive power, amount of energy per unit area, which is given by sigma epsilon Ts to the power 4. Also there is convection. Ts is there, H is there, T infinity is there, convection is there, radiation is there. These both are contributing to the heat transfer from the surface. What is G? G is energy coming from other surfaces to this surface. So if I have, I am sitting in a room, there is a furnace or a gas stove which is burning, heat is coming from there to me. There is a tube light or a fluorescent light, from there the heat is coming to me. Okay, so all sources of energy which is giving heat to me is this G. What is going out from me is real surface emissive power plus the convection component, which I said while doing convection also. Natural convection always exists. So that value also has to be added. So G is called as irradiation, rate at which radiation is incident per unit area of the receiving surface. G absorption is the portion which is absorbed by the surface. We will see details of it in the topic on radiation. Absorption means 100 watts is coming to me, how much I am taking in, which causes an increase in my temperature. That is called as absorbed energy. Suppose I take 20 watts in, the temperature would rise by a certain amount. Suppose I took 80 watts in, then large amount of heat has gone in, so temperature will rise a little bit higher. Okay, and this we have one problem. Same human body problem. Now you have emissivity taken as 1. So you are supposed to calculate the energy transfer by radiation. There is a typo here. This is not equal to, it's a multiplication. So epsilon sigma As into Ts to the power 4 minus T infinity to the power 4, we give 115.8. Let's just go back, and we said 180 watts is by convection, which is typically natural convection. 10 watts per meter square Kelvin is natural convection. Let's go back here. Natural convection value 10. 2 to 25 is for gases. For simple air, 10. So 180 watts is by natural convection. 115 is by radiation. So you can see these two numbers are almost balancing each other, meaning 300 watts is the total energy, out of which 40% roughly is by radiation, 60 is by natural convection. A very, very important point from this example is that whenever radiation is there, natural convection contributes almost equally. Therefore, you shouldn't be neglecting natural convection, especially when you have radiation problems. When you have radiation problems, natural convection heat transfer may account for about equal amount or around equal amount of energy transfer as compared to radiation. Okay, so this is a summary, you can take a look at it. Conduction, convection, radiation. Sigma epsilon Ts to the power 4, when epsilon is 1, it is for a black body, otherwise it is a real surface. And H is the heat transfer coefficient. These are all given in terms of fluxes, watt per meter squared. So Q double prime represents heat flux. E here represents the energy transfer, which is again a heat flux. Okay, so when you want the total energy, you multiply by the surface area available for heat transfer. In the next module, we will go ahead and deal with how to obtain the conservation of energy equation on a rate basis for a control volume. Thank you.